Okay, start recording. Okay, let's start our Zach seminar. It's my big pleasure to introduce John Lesieutre from Pennsylvania State University in the United States. And John will speak about Tri-Coble surfaces.
All right, thanks a lot for having me here. So let me just start off by kind of introducing the problem. Hope this talk is going to be kind of the construction of an example, and I think it's fun. But let me show you the question. So what I'm going to do, the main result is I'm going to tell you a rational surface that has automorphisms that don't have any periodic curve. So there's no curve that gets mapped to itself. But the construction is very, very classical. It's based on properties of the Bertini involution and Coble surfaces and other things from long ago. And I think everything here really could have been done 100 years ago. There's not going to be any high-tech geometry at all. So before I get into it, I know these rational surface automorphisms are maybe not a very familiar thing. So I want to just start off telling you one kind of famous example of a rational surface automorphism to kind of set the stage for the question. So let me draw a picture here. So let's say, look at the map from P2 to P2 that's just given by the standard Cremona involution. So I'm going to invert all the coordinates. It's a famous map here. I better label P2 or you won't know. All right, so this map has three indeterminacy points, right? The three standard coordinate points. But maybe if you blow up all 3 points, the map, this is just a birational map, but if you blow up all 3 points, it resolves the map and you get an actual automorphism of this blown up surface. From my point of view, this is not such an exciting automorphism today. It's an involution, and we're going to be looking at automorphisms that have infinite order. Anyway, if we blow up the 3 points, we get an automorphism. But here's what I want to imagine now. So imagine that we blow up not just those 3 points, but we're going to blow up some additional points also. So I'm going to take these 3 points, and then I'm going to throw in, let's say, r minus 3 more points. So I have a total of r points blown up now. And what happens if I sort of follow these new points under the Cremona involution? So on the other side, I guess the important thing to realize is that the points on the left and the points on the right are not the same configuration. So I still get if I blow up all these points, I get a map from one rational surface to another rational surface. It's an isomorphism, but these are generally sort of 2 different rational surfaces, right? For example, if 3 of these green points that I blew up were collinear, after you apply the Cremona involution, they're not going to be collinear anymore. So generally speaking, when I do this, I get an isomorphism between 2 rational surfaces, but they're different rational surfaces because the configurations of points we've blown up are not the same. Okay. On the other hand, imagine that you tried to not just blow up these r points at random, but you tried to choose the points very, very carefully. So you can imagine it could happen if I chose these extra green points just right, that this new configuration I get, although it's sort of, the points get moved around, maybe they are equivalent up to the action of PGL2. So if you choose the points very carefully, maybe this new configuration of points will be really the same thing as your original configuration of points. So maybe there's some linear map in PGL2 that maps this configuration back. So if you could arrange for this to happen, so now you'd have this isomorphism from the surface to itself that's order 2, but you can imagine kind of composing the Cremona involution with a linear map. And now you'll get an automorphism of a rational surface of infinite order. So let me kind of write this out without the picture, and maybe that will make more sense. So I'm taking P2, I'm blowing up a configuration of points in P2. Sorry, too many words on this one. So applying the Cremona involution to 3 of the points that you blew up kind of moves around the other points. But imagine that you chose the points just right and that the new configuration you get is actually equivalent to the old one up to some element of, sorry, PGL3, I'm in P2, up to some element of PGL3. So now I could, I originally have a map from the blow up at this first configuration P to the blow up at the second configuration Q. If P and Q are equivalent under PGL3, then I can compose with this linear map L, and I'll get a map from XP to XP. And this will be an automorphism from one rational surface sort of to itself. And in this case, typically the automorphism you get is of infinite order. So although the Cremona involution gave us a blowup of a rational surface with a not very interesting automorphism, it was just finite order. This kind of construction will give you infinite order automorphisms. The hard part here is that finding points that are, where applying the Cremona doesn't change their sort of, what configuration you have in the moduli space is very tricky to find these points. They're quite special, these configurations P. So this was carried out by Bedford and Kim and by McMullen. I should probably also mention Uehara has taken this even further, of finding these configurations of points P where you can get an automorphism in this way by composing the standard quadratic involution with a linear map. So these are the kinds of maps we want to imagine. They're kind of infinite order automorphisms of rational surfaces obtained by blowing up many points. It's not just finite order things on a Delpezzo. Okay, so here, well, let me say a little more about this. So how do you find these points that are invariant? The idea is that if you pick your configuration P, where all the points in the configuration P lie on a cuspidal cubic, finding these invariant configurations is going to be a lot easier. So the way that Bedford and Kim and McMullen were able to do this was by specializing the points, by not using really random looking sets of points in the plane, but rather specializing them to a configuration where finding these invariant configurations is easier. But kind of an artifact of doing the construction in this way is that you end up with an automorphism that leaves the cuspidal cubic invariant. So here's the question, based on this construction I mentioned, around that time, maybe 15 years ago, there were a lot of new constructions of rational surface automorphisms, but the vast majority of them had the property that there was always this invariant curve. So the question was posed by McMullen and by Harborn, can you find an automorphism of a rational surface with no invariant curves? So they specified a positive entropy automorphism. What that means is that if you look at the pullback map on N1 of X, so this is just a linear map from a vector space to itself, positive entropy means that has an eigenvalue bigger than 1. But I think even if you forget that, if you don't know what that means, just change the question. Can you find an automorphism of a rational surface with no invariant curves? Just, this arose from the fact that all the known examples people were coming up with did have invariant curves. All right, so McMullen's question was answered fairly quickly by Bedford and Kim, who showed, essentially they showed you could use that construction I just mentioned and use a computer to solve for the point configuration. And the computer is able to find configurations that work and where there are no invariant curves. But it's a kind of tricky computer calculation. It involves taking the intersection of some degree 50 curves in the plane or something like that, and finding one of the intersection points. So the computer will do it, but it's hard to really get your hands on it and write the map down. So after that, McMullen kind of changed the question and asked, can you find a synthetic construction of an automorphism of a rational surface with no invariant curves? So what a synthetic construction means, I think, is in the eye of the viewer, really. But basically, it's a question, can you do it where you don't need a computer, where you can really get your hands on it and see what's going on? And that's what I want to give you today. So I'm going to give a synthetic construction of an automorphism of a rational surface with no invariant curves. Comparing it to, we have the advantage of already knowing that these things exist. So it helps to have this Bedford-Kim example in the background. But this one I think is still interesting because it has some quite different properties from the Bedford-Kim example. So the map they give is a degree 2 map, right? It's just a quadratic map contained with a linear map. The map I'll tell you today is a degree 377 map with no invariant curves. But in other ways, the map I'll show you is simpler. First, because you can write it down without any computer assistance, really. Another thing is that the automorphism group with no invariant curves is pretty big. It's most of a free product of 3 Z mod 2s. And in the other example, you only get 1 map. So I think it's good to have 2 examples now and they're quite different in character somehow. Yeah, let me say if I went too fast in the construction, which I think I probably did, I'm not going to come back to it again. So we're going to do a totally different construction now. But any questions up to here?
It's positive entropy and invariant. I mean, it's entropy and invariant of maps, or
Yeah, that's right. So the entropy is an invariant of the rational map.
okay.
Yeah,
Can you
so
say
I mean,
what it
you
is?
can just read positive entropy as infinite order if you want, maybe, if it's not a, I mean, or just forget it. I think finding an example that's not positive entropy is probably actually a lot harder than finding one that is.
And about the Bedford-Kim construction, you say, oh, you can do it using computer, but as I understand, this depends on the number of points you choose.
Yeah, that's right. So they have an explicit example where you blow up 11 points.
So the construction works for some points, but not for any choice of points.
Yeah, I think for any number of points R, you can probably use their computer program to find a construction that works for that number of points. I don't think they have a way to see that it works for any number of points, but I don't have that either. So
Oh, I
it might
see.
be an interesting question going forward. Yeah, mine's going to be specifically a 12-point blow up of P2 that we'll look at.
Thank you.
All right, so let me tell you this strategy here. Well, okay, before I tell you the strategy, let me tell you some things you can't try. You can't use a surface where there's some effective anti-canonical class or even pluri-anti-canonical class. So a Del Pezzo surface won't work. A Coble surface won't work. Any automorphism of a Del Pezzo surface is going to have an invariant curve. And the reason is, if you just look at the pullback, if you have an automorphism of a surface, it preserves the canonical class. So it's going to preserve this linear system minus MKX. So, right, minus MKX, this is a projective space PR for PR. So the pullback gives you kind of an automorphism of this projective space. An automorphism of a projective space is always going to have a fixed point. And that fixed point is an invariant curve or a periodic curve. So anything with non-empty anti-canonical will work. So Del Pezzo's never gonna find one there. Coble surfaces, which I'll define later, also not going to work. Another thing is that if you have a finite order automorphism, of course, there's always going to be periodic curves. Every curve is periodic. This is maybe a good chance to point out, though, that if C is a periodic curve, meaning that Fn of C is C, then you can just take the union over all n of, well, maybe I should call it J. I could just, if I have a curve that's periodic, I can get a curve that's actually invariant by taking the union along its orbit. So most of the time I'll talk about, if I can prove that there's no invariant curves, that proves there's no periodic curves, as long as I don't make any kind of irreducibility assumption. So I'll probably be a little sloppy in my speaking and sometimes say invariant and sometimes say periodic. But if there's a periodic curve, then there's an invariant curve. So as far as I'm concerned, we might as well just look for invariant curves. All right, so again, Del Pezzo's no hope, finite order maps, no hope. We're going to need to look at these kind of infinite order, blowing up at least 9-point type rational surface automorphisms that I gave at the beginning. So here's the basic strategy. So imagine that I already have an automorphism of a rational surface X. Now, if that automorphism has a fixed point, and typically these things have many fixed points, always, I mean, they'll have some fixed points. If you blow up the fixed point, you still get an automorphism of the blow up, right? The fixed point, the point, when you blow up the point, it's parameterizing tangent directions at the original point. So the action on the tangent space on your original surface just gives you the action on the exceptional divisor. So if you blow up a fixed point of a surface automorphism, you still get a surface automorphism. If you blow up a non-fixed point, that won't be true anymore. Your map will become indeterminate at the pre-image of the point you blew up. But if you blow up a fixed point, you're safe. Blowing up a fixed point of an automorphism, you still get an automorphism. So now imagine that we were in the following situation. Maybe I had two different configurations of points P and Q, and I had an automorphism phi P from the blow up of P2 at the configuration P, and another automorphism phi Q from the blow up at the configuration Q to the blow up at the configuration Q. Now, if you manage to set things up so that your phi P automorphism fixes all the points of Q, and your phi Q automorphism fixes all the points of P, then both those automorphisms will lift to an automorphism of the total blow up, where you blow up all the points, right? Because phi p will lift because when you blew up the other points, you blew up a bunch of fixed points of phi p, so it lifts. Same thing with phi q. So they'll both lift to the blow up. So that means that on this common resolution, you'll have two different automorphisms. Even if both of them have invariant curves, you wouldn't really expect the composition to have any invariant curves. Only if something weird is going on would that happen. So the idea is we're going to find automorphisms without invariant curves exactly this way. We're going to find multiple configurations, P and Q, where each automorphism fixes the blown up points of the other one. Then we're going to take the total blow up. We'll have a bunch of different automorphisms upstairs, and some compositions of those will have no invariant curves. I should mention here a similar strategy is employed by Jeremy Blanc to construct some surface automorphisms that have a curve of fixed points, where they leave a smooth elliptic curve fixed point-wise on a 10-point blow up of P2. So it's a similar idea, but we're trying to sort of achieve the opposite, that there's no invariant curves. On the other hand, this is going to be hard because I said before, finding configurations P where there's any interesting automorphisms at all is not that easy. Finding configurations Q where there's interesting automorphisms is not that easy. Now we're trying to find two different configurations, not only where there's automorphisms, but where each one fixes the blown up points of the other one. So we're looking for extremely special rational surfaces for this strategy to have any hope of working. But we're going to be able to do it using some fun classical things. So far, so good. Okay. So this is based on the Bertini involution. I'm trying to give a synthetic construction here, so I think having a very concrete definition of the Bertini involution is going to be helpful. So here's how Bertini describes it. He says, let's say you're in P2 and you have 8 points. So you can look at the linear system of all degree 6 curves that are double at the 8 points. And what Bertini noticed is there's actually a lot of these things. There's a 2-dimensional family of degree 6 curves that are double at 8 general points. But if you fix another point, that also go through Z, there's a 2-dimensional family. If I fix any random, so I have 8 points. If I pick some other point, and I'm going to look at all the degree 6 curves that go through my new point, I'll call the new point Z, and are double at the other 8 points. There's a 2-dimensional family of curves that satisfy this. You can just dimension count. All of them that go through Z also go through some other point. And that other point that's paired with Z is the image of Z under the Bertini involution. Let me just say this one more time, because this is the basis for the whole talk. So I'm looking at P2 blown up at 8 points. So I fix a configuration of 8 points. And now I'm going to, from that, get an involution of P2. So here's what I do. So the 8 points are fixed. If I want to know where a new point Z goes, I look at the linear system of all degree 6 curves that are double at the 8 points and that also pass through Z. There's a 2-dimensional family of those. All of those also go through some other point, I of Z. There's a second base point, and the Bertini involution is the map that exchanges those 2 points. All right, there's sort of more modern way to say this, but I think the concrete picture is more helpful for us, is that if I look at the blow up of P2 at 8 general points, and then I look at minus 2kx, that's the linear system of sextics double at the 8 points. If you look at the map given by minus 2kx, so this is a famous divisor that's ample but not very ample. So the minus 2kx gives a map to P3. It's a 2-to-1 map onto its image, which is a singular quadric cone. And the Bertini involution is the covering involution associated to that 2-to-1 map. But again, for us, we'll sort of fix 8 points. If you want to know what happens to Z, you look at all the degree 6 curves double at the 8 points passing through Z. There's a second base point, and that's the image of Z under the Bertini involution. Questions with that? So I'm going to use this involution the whole talk. So if I've messed this up, now's a good time to stop me. All right, it's not so bad. So here's the picture I want to think about now. Let's say that I have a cubic surface in P3, and I blow up 2 points on the cubic surface. I'll call them P and Q. So cubic surface is P2 blown up at 6 points. Now I'm blowing up 2 more points. So I again have a degree 1 Del Pezzo surface. My surface is P2 blown up at 8 points. So again, there's this Bertini involution. There's this unique automorphism of a general degree 1 del Pezzo surface. So in terms of this picture where I'm thinking of it as a 2-point blowup of a cubic surface, what's the image of the Bertini involution? Given a point z on the cubic, what new point does it get sent to by this involution? Well, according to Bertini's description, what we're supposed to do is we're supposed to look at the linear system minus 2kx. So we're supposed to look at all the things in the linear system minus 2kx that pass through z, and then there's supposed to be a second base point, and that's the image of the involution. Well, minus 2kx on a cubic surface blown up at 2 points corresponds to quadric surfaces in P3, right? The anti-canonical class on a cubic is just H, so the 2 anti-canonical class is 2H. So we're looking at quadrics. At those 2 blown up points, I need quadrics that are tangent to the surface at P and Q. All right, so what is the Bertini involution going to do to a point Z? Here's what it is. So I draw the plane that passes through P, Q, and Z, and I draw a conic that's tangent to the cubic. So the blue one is the cubic surface. I took a hyperplane section. The element of minus 2kx is a quadric surface that's tangent to the cubic at P and Q, and I want it to pass through Z. So when I pass to a hyperplane, I get this cubic curve, and I get a conic curve that's tangent to the cubic at P and Q, and that goes through Z, and then a quadric meets a cubic at 6 points. 2 of them are at P, 2 of them are at Q, 1 is Z. So there's 1 residual intersection point, and that 6th intersection point is the image of Z under the Bertini involution. So if you want to know the Bertini involution on a cubic surface blown up at P and Q, to figure out where Z goes, you draw the plane through P, Q, and Z. Now you have a plane cubic and a plane conic, and you take this residual 6th intersection point. That's the image of the Bertini involution. All right, so we're also going to want to know about fixed points of the Bertini involution. So what does it look like when Z is a fixed point of the Bertini involution on a cubic surface blown up at P and Q? Well, it just means that the residual 6th point of intersection is the same as Z. So in other words, if I have a cubic surface blown up at P and Q, Z is a fixed point, means that in the plane passing through P, Q, and Z, there exists a plane conic that's tangent to the cubic at the 3 points P, Q, and Z. Maybe I should say it might look a little fishy to you that the Bertini involution always sends a point Z to another point I of Z that's in the same plane as P and Q and Z. This sort of reflects the fact that the Bertini involution preserves an elliptic vibration. All right, so again, for the Bertini involution based at P and Q on a cubic surface, to fix another point Z means that in the plane spanned by P, Q, and Z, there's a conic tangent to the cubic at those 3 points. Right, and that's 6 conditions on a conic, and there's only 5-dimensional family of conics. So this is a special thing. So far, so good. All right, so let's try to construct some automorphisms now of infinite order. This is an involution. It's not going to solve our problems, but this is what we're going to need with the rest of the construction. Oh yeah, I was pretty pleased with myself for working this out for the cubic. I didn't think it was written down anywhere, but of course, even in English, it was known in the 30s, this description. I'm sure in Italian, it's in the 19th century, but I'm not very good at searching that. All right, so here's our first attempt to construct a rational surface automorphism with no periodic curves. So I'm going to fix a cubic surface S, and I'm going to try to find one pair of points P. So P is 2 points, P1 and P2. Q is another pair of points, Q1 and Q2. And I want to rig it so that the Bertini involution coming from the P points, right? If I take the cubic and I blow up P1 and P2, I want the Bertini involution on that degree 1 del Pezzo to fix the 2 points Q1 and Q2. And I want the Bertini involution when I blow up Q1 and Q2 to fix the 2 points P1 and P2. So if I could come up with a cubic surface and 4 points on a cubic surface with these properties, what would it buy me? Well, now I would be able to blow up all 4 points together. So now I'd have a cubic blown up at 4 points. I'd have 2 different involutions on the cubic blown up at 4 points. And there's no obvious reason why this would preserve, why would that have an invariant curve? It's a composition of two maps. There's no obvious invariant curves for, common to both of them. So you'd think that this should solve our problem. I was hoping it would solve our problem. So let's give it a try. Any questions on this strategy? So the problem now is, how can we do this? How can we find a cubic S and these two pairs of points, P1, P2 and Q1, Q2, where the P involution fixes the Q points and the Q involution fixes the P points? Oh, of course, we're going to use our description of fixed points of the Bertini involution that we just worked out.
Stupid question. If you take them collinear?
All 4 points collinear? Well,
No, 3. If you take, okay.
Yeah, so you're correct that that third point, if I take the line through P1 and P2, it will meet the cubic at a third point, and that is a fixed point. But then I think it's hard to pick the fourth point to make that work.
Okay.
That's it. It's a good question. There might be a better way to do this. I couldn't get it to work that way, though. All right, so let's draw a picture of when this is going to work based on our description. So the green thing here is a cubic surface, and the two purple points are the P points and the two yellow points are the Q points. And I want to know, under what conditions is it actually true that the Bertini involution for the cubic surface blown up at the two yellow points fixes both purple points, and the Bertini involution on the blow up at the two purple points fixes the two yellow points? So let's see what we can find out. All right, so I'm first gonna, can you see my cursor? Zoom half the time does and half the time doesn't. Well, if you can see my cursor. So let's first ask, does the Bertini involution at the two yellow points fix this purple point that's on the right here? So how do we figure out if the Bertini at the two yellows fixes that purple point? Well, we follow our recipe for fixed points. So we're supposed to draw the plane through the points P, the two base points of the Bertini involution, plus the point we want to be fixed, which is the purple point. So there's that plane. So we get a plane cubic by intersecting our cubic surface with the plane. So that's what this, it's a little hard to see here. I couldn't find a perspective that would make this work well. So there's a plane cubic in this surface in this plane, that's our cubic surface intersected with the plane. And for the Bertini involution centered at the two yellow points to fix the purple point means that there's a plane conic that's tangent to this cubic at all three of these points. All right, and there it is. In this picture, there is one. So I've drawn this red conic curve here. That is tangent to the cubic surface at all those points. So that's one of my fixed point conditions, is that in the plane through those 3 points, there's a conic tangent to the cubic at the 3 points. So what do the other fixed point conditions look like? Well, it's every possible choice of 3 points. You need that in the plane through those 3 points, there's a conic that's tangent to the cubic surface at all 3. Right? Each of the 4 faces of the tetrahedron contains 2 points of one color and 1 point of the other color. So each of the 4 faces of the tetrahedron is encoding one of our fixed point conditions. All right, so there it is. So what I've drawn here is I've drawn in each of the planes through 3 of the 4 points, I've drawn a conic that's tangent to the cubic surface at those 3 points. So this kind of red mess here, this is not just like a sloppy drawing because I wanted you to see through the sphere. I mean, this is 4 different plane conics, and each of those plane conics is supposed to be tangent to the cubic surface. So in order to find these 2 special configurations of points, that's what we're asking. We're asking that, in each face of the tetrahedron, there's a plane conic that's tangent to the cubic at the 3 vertices of the tetrahedron. And it can happen. I mean, in this picture, indeed, I have drawn one where it works. But the question is now, well, will this automorphism have invariant curves? Maybe before we even think about invariant curves, let's just think about how could this happen? How could you find a cubic surface and 4 points? It's quite a lot of conditions for this to happen. So how could we find these configurations where there are all 4 fixed point conditions are satisfied? All right, well, let me hide the surface for a minute. So we're asking for the cubic surface to be tangent to 4 plane conics. This is not a great picture. But what you might notice is that in this example I worked out, these 4 plane conics, they're actually all fit together into a sphere. So in fact, there exists a quadric surface in P3 whose intersection with each of the faces is the quadric in question. And that's one way that this could happen. So there's actually a quadric surface that's tangent to the cubic at 4 points. So anytime that happens, if there's a quadric tangent to the cubic at 4 points, then all 4 of the fixed point conditions are satisfied, because when I cut this picture that's on the screen right now with any of the planes going through 3 of the 4 points, I am indeed going to get a quadric that's tangent to the cubic at those 3 points, just because it's coming from this tangent space quadric. So the conclusion is this. So it's pretty clear that if you have a cubic surface with 4 points and there exists a quadric surface tangent to the cubic at all 4 points, then all your fixed point conditions are satisfied. The P involutions will fix the points of Q. The Q involution will fix the points of P. In fact, not only is this a sufficient condition, it's also necessary. So you can write down, it's not a lot of work. If you write down the formula, the only way that this could happen is if there exists a quadric that's tangent to the cubic at all 4 points. Basically, if in each of the 4 planes there exists this plane conic tangent to the cubic, then those 4 things are just the intersection of a quadric surface with the 4 planes. So let me sort of rephrase this in slightly more intimidating language. So imagine I have a degree 3 weak del Pezzo surface. So that's just a cubic, or maybe a resolution of a mildly singular cubic. And imagine I have 2 pairs of points P and Q on my surface. So the theorem is that the Bertini involution at the P points fixes the Q points, and the Bertini involution at the Q points fixes the P points if and only if there exists a quadric that's tangent to the cubic at those 4 points. And the thing is that a quadric tangent to the cubic at the 4 points corresponds to an element of the 2 anti-canonical system of the cubic blown up at 4 points. All right, I think this is kind of a cool condition for the existence of these fixed points. So the P involution fixes Q, and the Q involution fixes P if and only if the 2 anti-canonical system on the 4-point blowup of the cubic surface is not empty. Note that blowup, so a cubic surface blown up at 4 points is like P2 blown up at 10 points. It's a pretty complicated rational surface. It's not a del Pezzo. Minus 2k for P2 blown up at 10 points, minus 2k is typically empty. But if you pick the 10 points very carefully, it's not empty. All right, so yeah, like I said, I think this is a neat result, but I almost gave up when I found this, because the intersection of the quadric and the cubic is fixed by both involutions. Because it's a curve that's in an anti-pluricanonical class, it's automatically invariant by any automorphism. So there's no way this cubic surface blown up at 4 points could possibly have an automorphism with no invariant curves. All right, so back to the drawing board. We're going to have to try something else. Any automorphism of this surface will leave that curve invariant. And just to introduce the terminology, so a Coble surface is a rational surface X where the anti-canonical class is empty, but minus 2 times the anti-canonical class is not empty. So the sort of very typical example of a Coble surface is that if you take a plane sextic with 10 nodes and you blow up the nodes, then the strict transform of the sextic on the blow up belongs to the 2 anti-canonical class. So the example we just saw had a slightly different flavor, but I guess it's really the same thing. If you take a cubic and you blow up 4 points, if there's a quadric surface that's tangent to the cubic at all 4 points, then the blow up is a Coble surface. And there's a lot of other these. So there's some big work on the classification by Dolgachev and Zhang. We more or less know what these look like, but there's many other ones. If you take 6 lines in P2 and you blow up all 15 intersection points of the lines, that's another Coble surface. They found a whole lot of them. But the typical one to imagine is the blow up of a plane sextic with 10 nodes. I don't know, 10 nodal plane sextic sounds really exotic, but if you just take a rational normal curve in P6 and project it to the plane, you'll get one. It's not too hard to find these. All right, so what we found is that this strategy is not going to work, because if I took a cubic surface and I found these pairs of points P and Q where the P blow up fixes the Q points and the the Q involution fixes the P points, then the blow up is a Coble surface. And automatically every automorphism is going to have invariant curves. So what should we try next? So let's try using not just 2 pairs of points P and Q, but 3 pairs of points P, Q, and R, all on one cubic surface. Now to get all of these Bertini involutions corresponding to each of the 3 pairs of points, I need each of the involution to fix both points of both the other pairs. So the P involution needs to fix the Q points and the R points. The Q involution needs to fix the P points and the R points. The R involution needs to fix the P points and the Q points. So finding these points is going to be a pretty delicate problem. So according to our description of the fixed points, when does this happen? So we need to find a cubic surface S that contains 3 pairs of points P, Q, and R, such that if I look at the 4 points of P and Q together, there's a quadric surface tangent to the cubic at those 4 points. If I look at the P and R points together, there's a quadric surface tangent to the surface at those 4 points. And if I look at the Q and R points together, there's a quadric surface tangent at those points. It's a lot of conditions. Finding these points is a pretty delicate question. Maybe let me pause for a minute here for questions. Is our strategy still clear enough?
Just a reminder that all of this reminds me classical papers about automorphism birational of cubic surfaces of non-closed fields. They generated by, if Picard group is Z, generated by Bertini and Geyser. So in something, this is like between the same lines. Very similar.
Okay. Maybe I should
Okay,
think
we'll
about
talk
that
about
later.
it later.
Yeah,
So
that's a good question. I don't.
Just a remark.
All right, so I need to find a cubic surface S that has pairs of points P, Q, with now 3 pairs of points with all these tangency conditions. So you could just start with a cubic surface and try to solve for the 6 points by writing down equations. It's a bunch of high degree equations and a bunch of variables. I don't think it's going to work. So what I want to do is that instead of first picking the cubic and then searching for points, I want to start with the quadrics and then interpolate the cubic surface after we've already settled on what the quadrics are. So I want to find 3 quadrics where any 2 of those quadrics are already tangent at 4 points. And then I'm going to interpolate a cubic surface that's goes through all those 6 points and has the required tangency at all 6 points. So we'll forget the surface for now. We'll try to find the quadrics. The question is, can you think of a configuration of 3 quadric surfaces in P2 where any 2 of them are tangent at least up 2 points? All right, so, well, maybe I'll keep going. It took me a while to figure out how to do these quadrics. But here's one way to do it. So, here's 3 quadric surfaces in P3. If you squint at this picture, you can see that any 2 of these quadric surfaces are indeed tangent at a pair of points. The blue and red are tangent here, for example. The blue and green are actually tangent along a whole curve, but that's okay for us. So what I want to do now is I want to take a picture. I want to start with 3 quadrics like this. So between any 2 of these 3 quadrics, I have a pair of tangency points. So that if I could find a cubic surface that goes through this point where the blue and red meet, and the cubic has that tangency there, and it goes through a point where the blue and green meet, and it has the right tangency there. If I get the right tangency for the cubic surface at all 6 points, then I'll have found a configuration of the type that I'm searching for. So why should there exist a cubic? Well, once I find these quadrics, I have 6 points. I want to find a cubic with a prescribed tangent direction at each of 6 points. That's a total of 18 conditions on a cubic surface, but there's a 19-dimensional family of cubic surfaces. So good news for us. I mean, there will exist a cubic. In fact, there will exist a pencil of cubics that are going to work. So this is what I'm going to call a Tri-Coble surface. So it's a cubic surface blown up at 6 total points. So it's a rational surface of Picard rank 13. The condition is that if you pick any two of these pairs of points, if you pick the P points and the Q points together, there exists a quadric that's tangent to the cubic at those 4 points. That means that the blow up SPQ, because there's that tangent thing, is a Coble surface. So I'm asking that this is a cubic surface blown up at 6 points. It has 3 different contractions down to different Coble surfaces. If I just blow up the P and Q points, that's a Coble surface. If I just blow up the P and R points, that's a Coble surface. If I just blow up the Q and R points, that's a Coble surface. So this is some big rational surface. It contracts to 3 different Coble surfaces. But because all these fixed point conditions are satisfied, this total blowup of a cubic at 6 points has 3 different involutions. And the hope would be that, in fact, the composition of those 3 involutions has no invariant curves. And that indeed is going to work out. So this is our example of a rational surface automorphism with no periodic curves. Is you take this Tri-Coble surface where you blow up 6 very special points on a cubic surface. You get 3 Bertini involutions that lift to this blow up, and then you check that the composition has no periodic curves. So how do I prove that this crazy map has no invariant curves? If you're worried about positive entropy, how do we check that it has no positive entropy? That's easy. So we're just going to write down the pullback that this map gives on the Néron severity group. So here's the pullback matrix for the Bertini involution itself on a degree 1 del pet. So it's a degree 17 map. Bertini already knew this. It's not so hard to check it. I'm composing 3 different Bertini involutions. So I'm going to need to basically multiply together 3 matrices that look roughly like this. So here's the matrix for all 3 of those things multiplied together. So like I said, you can see right here, you put it in the computer, it tells you that this new map has degree 377. The eigenvalue of this map, the biggest eigenvalue is 55 plus 12 root 21. It's about 100, I think. So that tells you that the map is infinite order because its action on N1 is infinite order. How do we see that there are no invariant curves? Well, if there were an invariant curve, its class would be invariant under this big matrix, right? It would be in the one eigenspace under the pullback because it would pull back to itself. So we compute what's the one eigenspace of this matrix. And what you find is that the one eigenspace is one-dimensional. The only thing in the one eigenspace is the anti-canonical class. And it's very easy to check the anti-canonical class is not even a pseudo-effective class on this variety, so there can't be any invariant curves. If there were an invariant curve, its class would be in the one eigenspace, but the one eigenspace doesn't contain any effective classes. All right, so that tells us that this map has no invariant curve. So hopefully it answers McMullen's question. It's a synthetic construction of a rational surface automorphism with no invariant curves. So what else can we say about it? Well, I still need to convince you that these things actually exist, right? I think we have a pretty good plausibility argument for the existence just by, I drew a picture of some quadrics and we did a dimension count. There should be a cubic. You might worry though that maybe there is something weird going on. Maybe anytime you find 3 quadric surfaces that have these right tangency conditions, maybe all the cubics that have the correct 6 tangent planes are actually singular cubics, and then you can't use the Bertini involution, and the whole thing would not work. So I think the only way to actually check that these things exist, that they're not all degenerate, is to just write one down. And for this, it's easier to use the computer. So you would expect that the general one should have these invariant curve-free involutions. To actually check that there is a general one, probably going to want a computer. So here are a choice of 3 quadrics, 6 tangency points, and a cubic surface that has the correct tangent that's tangent to 2 of the quadrics at each of those 6 points. This looks like a big mess. I actually checked millions of configurations and pulled the one with the shortest equation written out as a string in a search. So I'm sure there's a more sneaky way to do this. But because you're getting this cubic as the solution to an interpolation problem, because you're specifying what its tangent planes are at 6 points, it's hard to get one with a really neat equation. Of course, you could try to start with the cubic and then solve for the points, but then I think you'll end up with the mess in a different place. Anyway, one can check with these 3 quadrics here and these 6 points and that cubic. All these conditions are satisfied. Everything that is supposed to be smooth is smooth. It all works out like we need it to. So let me say a little more about the geometry of these automorphisms. I think I claimed at the beginning that not only do we get one automorphism with no invariant curves, but we get a large group of automorphisms with no invariant curves. So how can we get our hands on this group? Well, it turns out that there's a 3-dimensional subspace of Néron-Severi that's invariant under all 3 of the Bertini involutions. On this 3-dimensional subspace, the intersection form has signature 1, 2, so there's an action on a hyperbolic plane induced by the involutions. You can write it down, and the involutions act by reflections in 3 disjoint hyperplanes on that hyperbolic plane. So if the fact that there's an invariant subspace that's 3-dimensional is actually pretty easy to see without a computer, although maybe, well, it's not so interesting for us. If anyone wants to know about it, I can tell you where these classes come from. But again, what we get from this is that the subgroup of the automorphism group generated by these 3 Bertini involutions is going to act on the hyperbolic plane given by just taking, well, because of this 3-dimensional invariant subspace. And we can use that to study, are there any relations between the involutions and so on. So here's a sort of picture of what we're looking at. So this is a sort of disk model of the hyperbolic plane in this invariant 3-dimensional subspace. Let me tell you what these different regions are. So right in the middle, this hexagon is, you can check by hand that every class in that middle region there, I'm not going to tell you what these curves are. It's easy to work out what it is. All the classes here are ample in that middle hexagon here. And what are these other regions? Well, the pullback by the first Bertini involution acts by reflection on this green arc. So what's up here is, the pullback of that ample hexagon by one of the Bertini involutions. Here's the pullback of the ample hexagon by another Bertini involution. Here's the pullback of the ample hexagon by a third Bertini involution. And so on in this way. So if you want to know about this little region up here, that's if you first pull back by IP and then you pull back by IQ or one of the other ones. So what can we see from this? The entire white region is ample classes. And you can see that there's no relations between the different pullbacks, right? Because you can see if you took any word in the IP, IQ, and IR, if you just took a product of them with never the same involution twice in a row, you're going to take this ample thing and it's going to sort of pull it out towards the boundary, but you'll never move back towards the middle. So there could never be one of these things that gives the same as the identity map, because if you pull back these amples by any word, you're going to move towards the boundary. So we get this picture shows that there's no relations between these Bertini involutions. Now you might be wondering, what are the blue parts? Well, these things are actually not ample. Any curve in here is negative on the sort of Coble curve for SPQ. So if I just blew up the P points and the Q points together, remember that's a Coble surface. There's there's an element of the 2 anti-canonical class, a sextic, that's tangent to the cubic at all those points. So curves in this region are negative on that Coble curve. All the blue regions, curves here are negative on one of the other Coble curve. Classes here are negative on one of the other Coble curves. Classes here are negative on one of the other Coble curves. And these smaller blue regions just correspond to the images of the Coble curves under automorphism. So anything in a blue region is negative on one of these images of a Coble curve under some automorphism. So it's not Neff. So we actually have a complete description of what the intersection of the Neff cone with this three-dimensional subspace is, it's exactly the white area. So you can see this very explicit Cantor set on the boundary of the Neff cone here, right? Each time we're removing basically the middle third of a white segment. And the Neff cone is exactly where the closure of the white area meets the boundary. All right, so again, what are the conclusions we're reading off from this hyperbolic picture? So we get a free subgroup of the automorphism group generated by the three Bertini involutions on this Tri-Coble surface. There's no relations. It's possible there are other automorphisms that don't fix that subspace V. I don't know. It's pretty unlikely, I assume. With a little more work, Serge Cantat told me how to do this. So you can see that actually not only does just the composition of the three involutions have no invariant curves, but unless you look at one of the 6 conjugacy classes of the involutions themselves, which of course have invariant curves, and the compositions of just 2 involutions, which have the Coble curves as invariant curves, outside of those 6 conjugacy classes, all the maps have no invariant curves. And so a consequence of that is that inside the automorphism group of this Tri-Coble surface, you can find a free subgroup of, you can find 2 elements with no relations and where nothing other than the identity in that subgroup has an invariant curve. So we're really getting not just one map with no invariant curves, but a quite large group of automorphisms with no invariant curves. So let me just kind of quickly recall the Bedford-Kim construction and this one, just to see that they're really different things. I mean, each one is simpler in some way. So their map was a quadratic map, degree 2, mine has degree 377. The dynamical degree of theirs, if you know what that is even smaller. It's almost it's the minimum that's known for a Picard rank 12 surface. On the other hand, this example we wrote down here with a little work, we were able to get everything to be defined over Q. There you end up in some weird number field because you're kind of brute forcing some polynomials with the computer. The Picard ranks, neither one is of minimal Picard rank. You might hope to do this in Picard rank 10 or 11, but we landed in 12 and 13. Their example, it's kind of surprising. It's completely rigid. So they used the computer, they solved for these configurations, and the solutions ended up being unique for reasons that are somewhat mysterious. In this case, we get a positive dimensional family of examples. So you remember there was a pencil of cubics that would work after we fixed the quadrics. So there's at least a 1-dimensional moduli space of these. If you do a naive dimension count, there's probably a 4-dimensional family of these things. I haven't really tried to check it. And again, there you get just Z as the group. Here we get a sort of bigger group. So I don't know. I don't think either one is really easier. This one you can draw a nice picture. On the other hand, that one's degree 2. It's hard to argue with that. All right, maybe this is a good place to stop. Thanks.
Thank you.
Thank you, John. Thank you very much. Okay.
Okay, do you do it or do I do it?
You do it.
Are there any questions? No? Okay, I have a question. So I've been thinking of things like this, like automorphism groups or rational surfaces. But I was more interested on groups, on surfaces whose groups were infinite but linear algebraic groups. So like, yeah. You think these techniques can be used to construct or classify them?
Oh, okay. I don't know. Maybe I can point out why. So, maybe you're looking at things like if you look at an elliptic curve cross itself and then.
No, I'm talking about. Okay, no, you go ahead. Actually, I'm interested in this as well. So, yeah, go.
So another construction of a rational surface automorphism is you take the self product of an elliptic curve with complex multiplication, and then you mod out by the diagonal action of complex multiplication. So and then you have to take the minimal resolution. So in this case, right, from the E times E, you get an action of GL2Z inside the automorphism group. In these kind of examples, this is another case where you do get invariant curves because this S has terminal singularities, and when you resolve it, the exceptional divisors show up in the canonical, in the anti-canonical with positive coefficient. So there you also get, these are surfaces of Picard rank 14 or 15 or something. Maybe you know better than I do. But in these kind of examples, you do end up with invariant curves. So yeah, I don't know any with a kind of linear group where you won't, but it's an interesting question. I don't know.
It's the this is the kind of occasion that I wish we were in person, because then I would stick to you for the next 4 hours talking more privately. Yeah.
Oh, I mean, we can talk. Well, yeah, I'll send you an email. Maybe we can figure it out. Yeah, I don't know. I don't really know that kind of examples.
Okay. It's okay. All right. Any more questions?
I have 2 questions. So one question is, some elements in Cremona rank 2 are not regularizable. All your discussion was about regularizable elements.
That's right. Yeah.
Yeah. And anything about non-regularizable?
Oh, I mean, finding a non-regularizable one with no invariant curves is probably not very hard, I would guess. I mean, the trick is to find one that.
Yeah. Okay. Is it like written anywhere?
You know that? I don't know. I don't think. Huh. I can't think of a place. Maybe one of the actual Cremona experts here would know. But I'm not sure. I mean, I just kind of guessed that if you take anything of. I mean, even for a generic quadratic map, does that have?
I don't think so. But I just want to look for the reference, so it's okay.
Yeah, I'm not sure. I'm not sure.
Question in the chat about positive characteristics.
Oh yeah, that's a great question. So yes, this whole construction works in positive characteristic, but that actually is an excuse for me to ask another positive characteristic question. So imagine I took P2 over a finite field and I blew up all the FQ points. So the automorphism group of this surface is huge. For example, the Bedford and Kim example is also defined over any field that's big enough to solve some polynomial equation. So, they have a bunch of equations that 9 points have to satisfy, and certainly they'll satisfy those points in positive characteristic too. And that means that some iterate of McMullen's map or of Bedford and Kim's map, is also defined on, well, so let's say you took the Bedford-Kim map from the blow up at some configuration in positive characteristic to the same blow up. Well, here's the thing, this map is infinite order on cohomology, so it's never going to end up being periodic. And in positive characteristic, right now this map might not fix all the FQ points of P2, but some iterate of it will fix all the FP points of all the FQ points in P2, just because there only are finitely many. So if you replace this with some iterate, it does lift to the blow up at all FQ points. But the funny thing is that all these different constructions, my construction, Bedford-Kim construction, McMullen's construction, Blanc's constructions, the abelian surfaces, if you take a sufficiently large finite field and you blow up every FQ point, all these different automorphisms lift to that single blow up. I mean, all of them are defined over some sufficiently large finite field, and all of them, if you iterate it, it lifts to the blow up. So the blow up of P2 at all the FQ points when Q is big is going to have some huge automorphism group, because every automorphism anyone's ever thought of is going to lift there. So what is the group? I mean, is it a finitely generated group, or is it some terrible thing? I have no idea.
It's a good question. Yeah, very good question. Okay, I have another general question. So what do you expect any problems like this, which may be interesting for you for threefolds?
It's a good question. So I actually proved a couple of years ago that if you have an automorphism of a smooth rational threefold, that has positive entropy, so the pullback map has an eigenvalue bigger than 1, then either it fibers over a surface, meaning that the threefold map, commutes with a surface map. So you could take the map I just gave you and cross it with P1, and there's an automorphism of a rational threefold with no invariant divisors. Well, okay, that doesn't quite work. I suspect you can get something, a threefold example like this. But in the positive entropy case on smooth threefolds, either fibers over a surface or it has an invariant divisor. So in dimension 3, there's some pressure in that direction, that there is an invariant divisor. This theorem, I don't know, it maybe sounds more interesting than it actually is. It only works for smooth, it doesn't work for terminal. So typically in the case of terminal threefolds, is there always an invariant divisor is a good question. I'm
Do
unable
you
to
really need
answer that.
rationality in the theorem, or just rational connectedness is fine?
Yeah, rationally connected is fine, certainly.
Okay, all good. I think no questions.